No? Okay. So one of the things I noticed when I looked at the agenda is that 3 of the 4 speakers in this session have something in common that you guys might not know about. So it's your quiz. If you can tell which 3 have something in common and what that thing is, I'll buy you a beer. So I'm going to talk to you about Shasta, which is our new system, which we've been talking about publicly. We talked about the hardware publicly last year, and we started talking about the software publicly just about a month ago. So I want to talk about that system. Some of you probably saw this talk 2 weeks ago in Shasta, but Rich is the only one, it looks like, so he can be excused. So this is an architecture that is designed in a way that's pretty different from what you've seen from Cray before. So this is the obligatory slide about who our customers are and why they buy Cray systems. I think the main reason the operational forecast centers buy Crays is still the reliability, that they're operationally proven. They have the reliability needed to get a very high percentage of the jobs done without an error so that they can meet their operational schedule. As Cray, we were always focused on performance, and we've got a set of software tools that help our customers optimize their codes and get better performance, and we have folks on staff to work with them. So we've got some pretty deep expertise in the applications in this area. About our recent wins in the last year, the most significant ones are that Meteor Swiss upgraded their system, and the U.S. Air Force, in partnership with Oak Ridge National Lab, is our first customer for Shasta in the weather forecasting space. So this is just a press release about the Meteor Swiss system. They're continuing with GPUs, as you've heard yesterday. So they've got 18 nodes, each with 8 NVIDIA GPUs. I think the challenges that you guys are facing, probably the biggest one from my point of view is the diversity of processors and the specialization of silicon to do certain things well and how to get performance portability in the face of this diversity. So we heard from Matt Norman yesterday about how he's working on that with E3SM. We heard lots of people talk about this. It's definitely something that people need to deal with. The other thing that we're seeing is this rapid increase in the amount of AI work and analytics work that's being done on supercomputers. And it needs supercomputers in part because you need huge amounts of data, and you need to move that data into the nodes and into the processors. But what's challenging is that the software environments that people are using for these are different. And this isn't just Python versus Fortran. The mode of working, using Jupyter notebooks, expecting interactive access, expecting a cloud experience, but also needing to run big HPC jobs. How do you do that? That was a big target for the Shasta architecture, for the software architecture of this new system. So how to deal with that is something I'll talk about. And then, of course, maintaining and improving runtime reproducibility is really important for the operational centers. So we know that there's all this diversity in processors and accelerators. And I just said, there's this increasingly heterogeneous workload with all of these different software packages that need to coexist and different ways of interacting with the systems. So I'm going to skip through these slides. I'm going to use this as an example to motivate why people need supercomputers for data analytics. Blue Waters, which is an old Cray system, a couple generations old, the first petascale system for NSF, is now the world's most powerful geospatial system. So we heard yesterday, I think somebody mentioned this, the Arctic Dam project, and now this new Earth Global project to develop these high-resolution digital elevation maps for first Antarctica and now globally. from imagery. So putting together different satellite images, figuring out where they overlap, and stitching all that together, just a huge amount of data, and they're doing that on blue waters. The thing that we're the most excited about is the 4 DOE systems, which are all going to be Cray Shasta systems, but they're all going to be different. Perlmutter at NERSC you heard about yesterday, that's going to have NVIDIA GPUs and AMD CPUs. Aurora at Argonne is going to be all Intel. Frontier at Oak Ridge you heard about yesterday, that's going to have AMD GPUs. And the latest one we announced is El Capitan for Livermore, and those CPUs and accelerators have not been selected yet. So they're taking an approach of deciding that later because things are changing so fast. So there's a lot of diversity, and you guys have a big task to get codes that are going to run well on all of these. You guys are up to it. The thing that we announced with the Air Force, we're super, super excited about. I know Wei is involved in the application work for that she talked about yesterday. So Oak Ridge did a procurement for the US Air Force, and they selected Shasta, and they'll be providing HPC as a service to the Air Force for their operational forecasting. So it's a different procurement model, and it's the first one of our new systems, so we're super excited about it. So let's talk about what Shasta is. It's a system designed to support lots of different processors, unlike our previous systems. It's designed from a data-centric point of view, and it's got a new interconnect, which I talked about last year, I think. So it's the Slingshot interconnect. You guys have probably seen this information, but it's got some new features that will help both HPC and the AI and data analytics. The traffic classes and quality of service in a high-performance interconnect is pretty new. I mean, Mellanox has this, but it's not typically used. And it's got a new congestion management feature that is, we heard yesterday that it's hard to, was it Chris who said, it was hard to do the optimization of something because the times were different because of the Aries network. So we have had congestion problems on Aries. We've worked a lot with the Met Office on identifying the source and the fix for that. But that process led us to develop a feature in hardware so that we won't have to keep figuring out how to work around congestion in software. I won't talk about how that's done, but there actually is public information about that out there. So I'm going to skip over these slides pretty fast because this is information that's almost a year old. So this is the interconnect features. I'll mention that it's Ethernet compatible, which is kind of strange at first. But we think this is really important for being able to handle moving the amount of data in and out of the system that people are going to need to be able to do in this new era. So you can connect this to your data center network, which is typically Ethernet, and you can use regular Ethernet protocols over that. You can use the high performance protocols within the fabric of the Shasta system, and you can use regular Ethernet either on the system or to connect to other things. So that's definitely different for us. Still focused on reliability at scale. What I really want to focus on in the talk, though, is the new information about our software and how we're planning to deploy this, because this is really different. And it's designed for these converged workloads and workflows, where in one workflow you have both analytics and AI as well as normal MPI HPC jobs. We're also seeing a lot of uptake of containers for packaging applications with all their dependencies in this field, and containers for other uses in enterprise. So we've got a couple different ways that we're using containers in Shasta. I won't talk about the API stuff because that's all about system management. But basically, we have this situation where one set of users or one set of workloads has one usage model and the other stuff has another usage model. So traditional batch schedulers like Slurm and PBS and Moab are the normal way HPC users use it, supercomputers. But the data folks that's not their preferred way of working. They're used to cloud computing. They use Kubernetes. So we wanted to be able to combine that on one system. And with Shasta, we're doing that. So whereas on the XC systems, you could run HPC-style containers through Shifter or Charlie Cloud or Singularity, we're really focused on Docker and Singularity and on the different orchestration layers for this. So people who want to run Docker-based workloads and orchestrate that with Kubernetes can do that on Shasta. You could run the whole system that way. You could run part of the system that way. It's up to you. And so if you want the system to look like a cloud, your sysadmins can set it up that way. If you want it to look like a traditional HPC system, then you can put all the resources under the control of a traditional workload manager like Slurm. And if you want to mix those, you can slide that dividing line to match your workloads. You don't have to have a fixed amount of this style versus that style when you buy the system. So it's super flexible with respect to how you manage access, how the users interact with the system. So this is our marketing slide about that, performs like a supercomputer, runs like a cloud. Because we're seeing a lot of organizations want to provide cloud computing to their users that don't necessarily want to do that in a commercial cloud, which has pros and cons. So different, paying out of operating expenses versus capital expenses, having a fixed amount of computing versus an elastic amount, and having control over your data. So for on-prem cloud, you can run this as a cloud system, but you can mix and match with the traditional HPC, and that's really different from what I think anyone else is doing, and it's certainly very different from what Cray's done in the past. So this is a slide that talks about the evolution of our software and what we've added. So I said we've added the Kubernetes container orchestration so that we have support for these converged HPC and AI workloads. We're also adding multi-tenancy and different ways of partitioning. So it's not as weird as Cray systems have been in the past, where the Cray Linux environment was what it was, and if your workload fit that well, like, okay, that was good. We still have the Cray Linux environment with all the features needed to get the low jitter environment and the high scaling that we've had, for a long time. These are things we've added on to it to support other workloads. And this is just another slide about that and how we think about this. So rather than thinking of login nodes and compute nodes, the system is designed to be presented as services. So it's a service-oriented architecture, and we can provide user access services, which are what happens on a traditional login node. But we can do those in Kubernetes and make that very resilient and elastic so that you don't have to decide in advance how many of those nodes you want. We can also do traditional login nodes if that's what you want, but the system's designed to be able to present login nodes or different services to users in a very flexible, resilient way. And the programming environments for traditional HPC with compilers and for the AI stuff, which to me is also a programming environment, also can be either containerized or bare metal. And so this is a pretty big change from what we've done in the past. It's super flexible, and it's going to let us keep up with the change in the community on the software and the way things are deployed, which is just changing super fast. On the left side, we've got the administration part, and that also is going to be completely different in Shasta than it used to be. It's also services, and there's well-defined APIs so that our customers can mix and match the elements that we provide with their own favorite tools, rather than being a monolithic stack. It's modular, and so you can replace different layers with the version of stuff that you like if you want to. I'd say the other thing is we've made it so that we've separated things out in a way that will let us not have to take the system down to make changes to the software stack. So instead of having to take the system down to change the operating system version, we'll be able to do that without taking the system down, and that's going to be pretty neat as well. So that's my last slide. We're really excited about Shasta. It's really designed for this convergence. We're seeing the DOE customers talk to us about their view of their workloads, and it really is converged, and so we designed Shasta to meet those needs, and they've bought 4 of them. So we're psyched.